Today we are going to do some calculus with vector-valued functions. Recall the definition of derivative that we had for our real-valued functions. So our derivative of function at x is going to be a limit as h goes to 0 of f of x plus h minus f of x over h. This is our way of turning slopes into an actual number or function for a given nonlinear function. What we're going to do now is use essentially the same definition for vector-valued functions. So here we have a vector-valued function r that uses a parameter of t. We still have our limit as h goes to 0. We still have a difference between our function at x, in this case t plus h instead of x plus h, and at t, and we still divide by h. We use the same notation of using a prime on our r of t, or we can also use dr dt if we prefer. Most people stick with the prime notation. Now, before we actually get started finding these derivatives, taking problems and actually working them out, let's make sure that we know what this means geometrically. So let's imagine we're in three-dimensional space. So we have our axes here. That should pass to the same point. R represents some curve doing something. I'm not sure what it's doing, but it's doing something. And we want to take a point, some t, that's on the curve. And technically this point is r of t turned into a point. We'll take some small h so that we're just a little bit away from that t, and that's certainly our t plus h. Now, do note here that I did draw what looks like a continuous curve, because it will turn out to be necessary that our curve is continuous in order to have a derivative in the first place. So I'm not even going to think about ones where that's not true. But now we need to think about what this format means. Think about what r of t plus h is, and think about what r of t is. Well, those are literally just the vectors that start from the origin and end at these points. So let's even just go ahead and draw those in here. So this is a vector r of t. Then we have, actually, let me move t plus h a little bit further away. Maybe that'll help a little bit. So let's say that's our t plus h instead. So this is our vector, r of t plus h. So we have two vectors pointing out to points on our curve. We can even name these points if we want to specify them as different from being r of t and r of t plus h. We could call this the point P and this the point Q. Now, what does it mean to take the difference of two vectors? Well, as long as their initial points are the same, really all that means is that we take a vector from the terminal point of one to the terminal point of the other. And we start at the one that is subtracted. So we're going from P to Q. I'll kind of draw it off the curve a little bit so it's a little easier to see. This thing here is r of t plus h minus r of t. It's a vector that points from a point on the curve to another point on the curve. Maybe I should have picked points where that wasn't so flat, maybe where it was a little bit more curved. But hopefully you get the idea that by taking that difference, we find what we call secant, or, well, you could say secant lines or secant vectors, I guess. But the point is that we are finding a vector from a point on the curve to another point on the curve. And if we look at what happens to this as we let h go to 0, the point Q is going to move towards the point P. I mean, we're saying here that it's continuous. That means as long as we move along this curve, we will end up at that point. And so this vector is going to get closer and closer to being a tangent vector to this curve. It's going to be closer and closer to being along a tangent line. Of course, as they get closer and closer together, this vector will get closer to being the zero vector, having a magnitude of 0. And so that's why we balance it out by dividing by h. This h is also going to 0, of course, because, I mean, that's what the limit's saying. And so those 0 over 0 will essentially cancel each other out, but they'll balance each other out, maybe is a better way of putting it. And so we get an actual limit. So overall, what we're going to get is a vector that is tangent to the curve at the point P. And so essentially, our derivative of our vector value function is playing the exact same roles as the derivative of a real valued function, in that it gives you the direction of the graph, except here our directions are going to be given in terms of vectors instead of the slopes that we were getting for our real value functions. So for this reason, as long as we're not getting the 0 vector, we call our prime of t a tangent vector to the curve. And we can also use the fact that we have a tangent vector and a point. So when we find the derivative at P, where we have a point already, and we can use that point and the tangent vector that we get to actually get a tangent line. So you could say here that well, I'd have to give a new notation. I'm using R for this curve, but if I wanted to use it for the line, I'd have to give it another name. Maybe we'll say L of t. L is our line. It's going to be our point. We could think of, actually, we can go ahead and actually even call this just R of t. And then we add some parameter, which we'll guess we'll have to use something other than t in here. Actually, yeah, let's say we pick a particular point, and we pick a particular t value. So for t equals a, so we plug in a into our original curve, our R of a. We add our parameter t times the derivative of the curve at a. So this is a vector that points in a particular direction that is tangent to our curve, and this is our point that we're plugging in. This is our tangent line, at least in vector form. Of course, we could put it into other forms if we prefer. Now, unfortunately, there is a slight problem when we're talking about r prime of t. The direction was quite important. It was a tangent to the curve. Unfortunately, the magnitude itself has more to do with the parameterization that we've used and less to do with the curve itself. We can have different parameterizations of the same curve and end up with the same tangent lines but different tangent vectors. Therefore, usually what we'd like to do, and this gets a little bit more complicated, so sometimes we don't bother to do it, but a lot of the times when you're actually trying to work with the curve itself and not necessarily with the parameterization, we like to turn these into unit vectors. So we will say the unit tangent, vector to the curve is the vector where we take r prime of t and divide out its magnitude. This gives us a unit vector, at least as long as we're not dealing with a place where r prime of t is 0. If we add a zero vector, this kind of process actually breaks a little bit. But there's reasons for why it breaks. It doesn't just arbitrarily break. There is a reason for that. Usually we use the notation of capital T of our parameter little t, the capital T here standing for tangent. We will see in a later section, I think it'll actually be the next section, a similar notations for other vectors that have to do with our curve. And t is just going to be one of those vectors. But it's the easiest one to find, of course. This unit tangent is mostly unique. It's not completely unique because if we have a point on a curve and we want to talk about its tangent vector, we could be talking about this direction, maybe that's our t, or it could be looking at the other direction. That has to do with the orientation of the parameterization. So we're not quite getting away from having to know something about the parameterization. But as long as our curve has arrows on it, if we've specified a parameterization, this unit tangent will be unique. So that's one of the reasons why we like to denote what parameters, what orientation that we're using for our curve, because it does allow us to specify particular unit tangent vector, and it'll actually allow us to specify the other vectors that we'll run into next section as well. So that now that we know what the derivative of a vector valued function means, how do we find the derivative without having to resort to the definition every time? We kind of introduced a definition for real valued functions, and then as soon as we could, we developed rules to kind of not have to ever look at the definition again unless we're in a completely unique situation. So we want to actually do kind of the same thing here. Well, it turns out it actually is as really simple. Just like with limits, we can take the derivative of a vector valued function by looking at the component functions. So here, if we have a vector value function r that has components of functions of f, g, and h, then the derivative of r is just the derivatives of our component functions put together into another vector valued function. It turns out that all we really have to do to take derivatives of vector value functions is take derivatives of real value functions. So we're just essentially doing the normal Calc 1 stuff, but in this case, three different times. If we were working in 2 dimensions, we'd be doing it twice. So it's more just that we're repeating the stuff we already know how to do rather than having to learn a brand new thing. And this is actually really easy to prove. Let's think about what r prime of t means, going back to our definition that we just introduced. I'm going to go ahead and use the letter k instead of h because they're using h here for a component function. So I'm going to say the limit is k goes to 0. We have r of t plus k minus r of t all over k. Now I replace r with its component functions. Make sure I keep that limit in here. But r of t plus k just means f of t plus k, g of t plus k, and h of t plus k. Then we subtract r of t is just exactly this up here. So f of t, g of t, h of t. This whole thing is still over k. Then we go ahead and just use the rules for the difference of two vectors. So we're just treating this as two different vectors that we're subtracting, and then dividing by k, or in other words, we're essentially doing a scalar multiplication where we're multiplying 1 over k to that. So when we subtract them, we end up just subtracting components. So the f of t plus k will then be f of t plus k minus f of t, and then we will go ahead and divide that result by k. So kind of putting those together, we have, that's what I said for f. Then we had exactly the same thing for g. And the same thing for h. And now we actually have to look back at the last section. So we have a limit of a vector valued function. We can bring that limit inside and just take the limit of each of the individual pieces. So we have the limit as k goes to 0 of this fraction of f. And then we also have the limit as k goes to 0 of the other two. And then, of course, the whole point here is that this limit of f of t plus k minus f of t over k, that's exactly what we mean by the derivative of f at t. And again, this is the derivative of g at t, and then the derivative of h at t. So it's just a matter of all the operations that we're doing to the r's, we end up being able to bring inside of the vector, inside the angle brackets, and so we just end up getting the derivatives of the component functions. And do note here that what this basically means is that the derivative of r will only ever exist if the derivatives of the component functions exist as well. If these all three exist, then the derivative of r exists. If the derivative of r exists, then these three derivatives also exist. So it's an easy way of kind of just not even having to work with vectors if we don't really want to. Let's do some examples. So here's problem 5 from, we are working in section 13.2, so this is on page 900. Actually a really nice even number there. But we have a vector value function. This one's in the plane, so we only have two components. But its first component is e to the 2t, and second component is e to the t. We want to find the derivative of this, and we want to sketch everything that's going on, so we can get an idea of what's really happening here. We'll get to the sketch in just a moment, but let's first find the derivative. And note here what's going on. All we need to do, we don't have to differentiate the entire thing all at once. We can focus on e to the 2t and ask what is the derivative of that. Of course, with e to the 2t, we do need to use the chain rule. We need to differentiate e to the whatever is just still e to the whatever. So we'll still have it e to the 2t, but the derivative of 2t is 2. So we'll have 2 times e to the 2t still times I. Or we could write this with angle brackets if you prefer. Then we need to differentiate e to the t. Of course, that one's even easier. Just e to the t, still times j. And then we might as well go ahead and plug in our t equals 0, because they'll want us to plot these points. So r prime of 0. We plug 0 into e to the 2t, we get this just turns into a 1, so we're left with a 2. And then this just turns into a 1. So I'm going to go ahead and write this in angle brackets. Of course, the original function at 0, if we plug in 0 here, e to the 2t is 1, e to the t is also 1. So we're plotting these two particular vectors. So let's go ahead and do that. Now here, I do actually want it to use the name of r. So I'm going to put r with a colon that will immediately assign the curve that we put the name r. If left to its own devices, GeoGebra would probably pick A for this one. So we have e to the 2t, e to the t. Remember, our variable here is t, and we have to tell it that. And then we need to pick some limits for t. Let's just pick a nice big range of 10 to, or sorry, negative 10 to 10. And, oh, oops. Want a parentheses, not an angle bracket. And this is the curve that we get. If we go ahead and we want to, okay, sorry. Let's first plot the point when we plug in 0. So r of 0. It's this point here. And I don't really need the name of it written on there. In fact, let's go ahead and zoom in a little bit. We can even go ahead and put in the vector that points from the origin to this particular point. We just do that by putting in vector and then giving it a particular point. So I could either type in A, and that would point to the point A because it's named that point A. We could also just go ahead and put in the r of 0 that we use to actually make that point. Or if we didn't want to pick a already predetermined point, we could give it a point by just putting in additional parentheses of, say, 1, 1 or 1, 2 or whatever. But here I'm just going to put vector of r0, and that gives me a vector that points from the origin to that point. And let's get rid of these names. We don't need the names on there. They're kind of cluttering things up a little bit. Now we also want to plot the tangent vector at this point. So if we look back at what that was, so we know that was 2, 1. We could just go ahead and put in 2, 1. But GeoGebra actually is pretty handy here. We could actually ask it to plot the vector r prime of 0. That will go ahead and plot the vector. Unfortunately, when we do that, it does always put it at the origin, starting at the origin. So we want this vector attached to that point if we wanted to actually see what it was. There's a number of ways that we can do this, but what I like to do is go ahead and take vector, and instead of giving it one input and having it automatically take it from the origin to whatever point we're talking about, we can actually give it 2 points, and it'll give us the vector from that point to the new point. So we want it to start at r of 0, because that's the point we're starting at here. Then we want it to end at whatever point we get by essentially adding on the tangent vector to that point. So we're going to take r of 0, and we're going to add r prime of 0. And then it'll essentially take these two vectors and add them together to get the terminal point of this vector when we plot it. Again, we don't need the name on there. And so that's what we have. This vector has the magnitude and direction that corresponds to 1. So it goes 2 units over in the x direction and 1 unit up. But it's starting at this point, which is what we really wanted to show. And note that really does actually agree with the curve as we see it there. It is very much tangent to the curve at that point. So it's a nice visual representation of what we've been talking about. Let's do another one. So here, it's the same directions, but we just have a different curve. It's still in the plane. Now we're dealing with 4 sine of t as our first component, and don't forget the minus sign here. It's negative 2 cosine of t for our second component. We do exactly the same kind of thing. We're going to take the derivative of this. Derivative of sine is cosine. The 4 just kind of comes along for the ride. We didn't even have to worry about the stuff that's in front of the j when we took this derivative. It's just do it by itself. Now we look at negative 2 cosine t. Derivative of cosine is negative sine. They'll actually get rid of the minus sign, so we get a plus 2 sine t. Of course, then we also want to go ahead and plug in our point. So let's go ahead and plug it both into r and r prime. So r of 3 pi over 4, sine of 3 pi over 4. Got to kind of think about that a little bit. It turns out to be square root of 2 over 2. Think about pi over 4 gives us square root of 2 over 2. Mostly what we have to do here is remember whether or not it should be positive or not. For sine, it will be positive, because sine is positive in the second quadrant. So we end up with sine of t is square root of 2 over 2. Of course, we're multiplying it by 4, so that's going to go ahead and turn that into a 2 square root of 2. Let's actually just put this in angle brackets. Then cosine of t, if we put cosine of 3 pi over 4, cosine is negative in the second quadrant. So this time it's going to be a negative square root of 2 over 2. Of course, we have a negative 2 already, so that's going to cancel out the negative and the 2 on the bottom, and just give us a square root of 2. Do the same thing for r prime. Just plugging in the same 3 pi over 4. We actually get to use the same ideas that we had when we plugged it into sine and cosine, but now essentially the sines and cosines swapped each other. So here, now we're going to replace this with a negative square root 2 over 2, which combines with the 4 to give a negative 2 square root 2. And then the sine here is going to become a square root 2 over 2, which the 2 will just go away. And we don't have the minus sign either, because that went away when we differentiated. So we still get square root of 2 for that one. So let's go ahead and plot this thing. So the curve R is going to have components of 4 sine of t and negative 2, don't forget the negative here, negative 2 cosine of t, variables t, and since we're using trig functions, let's just go ahead and put from 0 to 2 pi. As you can kind of tell, if you remember, this is an ellipse. It's basically just an oval. Though we didn't, yeah, it's an ellipse. Let's just leave it there. We're going to go ahead and put the vector going to r of 3 pi over 4. So we can't just plug in 0 here. We're putting 3 pi over 4. That's the vector that points over to here. And in fact, let's go ahead and just plot the point. Oops, there we go. And we don't really need all the names in there. Okay. So our point is here. We have a vector going from the origin to that point. That's our r of t, or r of 3 pi over 4. We go ahead and plot the vector from starting at the point, so r of... Actually, I'm just going to go ahead and type in a. So a is already r of 3 pi over 4, so I can go ahead and just use it in here and not have to retype that whole thing in. I'm going to take the terminal point to be a plus whatever my derivative is, so r prime of 3 pi over 4. Over 4, not 74. And that gives me a vector that is tangent to my ellipse. It really is just tangent to the ellipse and points this direction. And you can actually tell from this vector what the orientation is. You might be wondering, if we're using these parametric equations, what direction do we travel around the ellipse? Well, now we have our answer. It is pointing in this direction. We're following that arrow as we go around. And in fact, if we picked another point on here, I mean, we could even just go ahead and plug in other points if we want to. So let's say, I don't know, I don't even have to put in something in terms of pi. Let's r of 4. some random, not so random, but it's a point over here. And then I can go ahead and look at the vector that starts there. Say r of 4. We take r of 4 and then we add its derivative to get the terminal point. And it's another tangent vector at this point, pointing in this direction. All the tangent vectors end up pointing in a counterclockwise direction. Okay. So pretty easy to see. I mean, technically here, if I was asking you to do this on exam, you'd have to go ahead and figure out you'd have to go ahead and find out the vectors this way, and then go ahead and graph them using those results. GeoGebra kind of does allow us to skip some of that and does it for us. It automatically computes the derivatives and plots them if you ask it to. Kind of cheap, but oh well. At least it gives a good representation of what we're really talking about. And that's the important thing. Let's also do this one. So problem 19. So here we're actually working with something that has 3 components. So this is a space curve and not a plane curve. Most of what we're going to be doing here is going to be very similar. And we'll go ahead and sketch this like we did on the previous 2, even though it doesn't really ask for that. But we have this formula for r of t. Ultimately we do want the unit tangent vector, but we find the unit tangent vector by just differentiating first. So the derivative of this, again, we just differentiate each of the component functions just separately. Derivative of cosine is a negative sign. Derivative of 3t is just 3. Don't forget our I, j's, and k's. Then we have sine of 2t. Here we're going to have to use the chain rule. So derivative of sine is cosine. But we have cosine of 2t. Derivative of 2t gives us another 2 that's outside, which will combine with the 2 we already have. So we end up with a plus 4 cosine of 2t, and don't forget your k. Now, what they're not actually even asking us to find the full capital T of t, so we don't really have to find the magnitude of this vector as it sits already. We might as well go ahead and find well, actually, maybe I should write it down here. So remember, capital T of t is r prime of t over the magnitude of r prime of t. If we're only looking for the unit tangent vector at a particular point, in this case t equals 0, we're looking for capital T of 0, which is r prime of 0 over the magnitude of that. So rather than trying to find the magnitude of this general formula, let's just go ahead and plug in 0 right away. So r prime is 0. So sine of 0 is 0. So actually that part we can even completely get rid of. Or we can go ahead and write in angle brackets to specify that the first component is 0. The third component is always 3. In fact, that doesn't depend on what t is in the first place. And then cosine of 2t, if t is 0, cosine of 0 is 1. So we have 4 times 1. The magnitude of this thing, which remember we just find by taking the square root of the squares of the components, using the Pythagorean theorem or distance formula, however you want to state it. If we work this out, we end up with the square root of 25, or in other words, we just get 5 out. They picked a nice number for us. So really all we're doing is taking the vector 0, 3, 4 and divide it by 5, which actually some people will leave it written like this, or maybe move the 5 to be a 1/5 in the front. Or if you really prefer, we can move the 5 inside. This is 0, 3/5, 4/5. And that's our unit tangent vector. That's a unit vector tangent to the curve pointing in whatever direction, whatever orientation our particular vector value function, our parameterization of the curve, is actually moving. So let's actually look at the picture of this. So again, I'm going to call my curve R. I need to write in 3 components. My first component was cosine of t. Second component is 3t. Third component is 2 sine of 2t. Obviously, our variable here is t, and because of the 3t in the middle, I'm going to go ahead and pick a broader range than just 0 to 2 pi. Let's just pick negative 10 to 10, and that'll probably be more than sufficient for us. So it kind of looks like we have a sine curve, but if you look at it from this angle, you can kind of tell that it does kind of go back and forth. It doesn't actually just follow the y-axis. The y-axis is the green one. But from some angles, it looks like one sine curve, and from another angle, it looks like another sine curve, and from some angles, it just kind of looks a little bit weird. It's going in some weird directions. Now, of course, we're mostly concerned about what happens at t equals 0. So if we go ahead and plot r of 0, we get this point here. So the a that we have here is the point that we're talking about. Of course, we can go ahead and put in our vector that points from the origin to there. Well, it might be a little hard to see against the red x-axis. We can go ahead and put it in our vector starting at our point. So our point is a. Then we're going to take a plus our derivative. I'm just going to go ahead and put in the actual vector that we found. We just use parentheses for this. So our vector was 0, 3, 4. And we end up with a vector that you can tell is parallel, or not parallel, it's tangent to the curve, pointing off kind of along the curve. So we can kind of tell that we're following the curve in this direction, and it's pointing off in that way. Of course, that doesn't actually give us the unit tangent. This is, we can even go ahead and label it. This is r prime of 0. That's r prime of 0. And that's not what we're looking for in the problem. We're looking for t of 0. We're looking for the unit tangent. So we do kind of the same thing. So we take the vector a from a to a plus whatever vector we're using. But in this case, our vector was 0, 3/5, 4/5. So we end up with another vector, which I'm going to go ahead and rename this one as well. So this was t of 0. So we have this long vector coming out. That is our actual tangent vector coming from this parameterization. But then we have the unit vector, because the magnitude of r prime of 0 may not mean anything to us. We could have a different parameterization and get a completely different magnitude to it. But as long as we're worried about the direction, the t of 0 gives us that just nicely. So in kind of a sense, the t of 0 is giving us our slope and not attaching additional information. Just like with our derivatives of real valued functions, the derivative just gives you a slope. It doesn't tell you anything about magnitudes or anything like that. So in a sense, this t of 0 is more related to the derivative of real valued functions than r prime of 0 is. Alright, so this video's ran on a little long, but we still have more to cover, so I'm going to talk about that in another video. So pay attention to that, and I'll see you then.